Hello and welcome to Chapter 4, the one where we do probability. My caution for you is that you've probably seen probability before or have dealt with it in simple aspects in possibly one of your classes you took before this one. So it's easy to dismiss it as something simplistic and that you maybe have dealt with before. My warning to you is that it seems like a simple idea until you start getting to all the nuances of what could possibly happen with it. So even if you've had probability before, I suggest you watch this whole video because I go through everything and it'll take you through all the possibilities. And then I have some additional examples after this video as well in case this one wasn't enough for you. And feel free if you need to, if you think you need more examples to ask, because I'm always willing to record more of these or meet with you in person. So let's do some probability. Really hoping that sound that just rang in my ears does not come through. Here we go. So notice that once again there's an outcome that exists in your textbook that we'll not be covering. The last one is Bayes' theorem. Bayes' theorem really only gets used in advanced statistics and stuff that we are not going to be doing in this class. So if you're curious, you can study it on your own. However, I will not be assessing you on Bayes' theorem because, well, it's not required for this class. And although I think Bayes' theorem is pretty cool, you know, I don't think it's something you need necessarily in your lives to confuse you a little bit when we're focused on only the things we need. So here we go. I've said that twice now. That's annoying. Anyway, so we're going to talk about the approaches to probability and how we assess them. You're probably used to what's called the classical approach and the subjective approach. And there's one more in there that you maybe haven't really thought about before, but it's more of the experimental approach. And then although outcome 2 and 3 just list two things, how to add and how to multiply, those two actually get pretty complicated depending on the situation you're in. So although those seem simple, they're going to be a lot of work. Let's get this party started. So first off, I want to get you down with the bare basics. Probability we like to think of as, chance or likelihood of something happening, where something can be one item or it might be 2 or 3 or 4 or any number. All probability values range between 0 and 1. So anytime somebody says that they are, let me stop myself here. I want to make a terrible joke, so prepare yourself. A lot of people talk about probability in terms of percentage when technically it's a proportion, so it comes out between 0 and 1. So what's interesting about this is when we get to classical probability, it'll be real clear on why it's between 0 and 1. But usually in our everyday vernacular and how we communicate with each other, we usually use percentages. So people will say, oh, there's a 30% chance of rain rather than a 0.3% chance of rain. Don't ask me why that's true. I have no idea. It's just something that's developed in the human condition of understanding of things. So there's that. But some of the probabilities that we will be looking at come from what are called experiments. So basically there's something that we call a random experiment where we don't know the outcome, so we consider it random. And so since it can't be predicted, we can look at it and say, oh, we don't know what the outcome is. Let's see what comes out of it. And often we'll repeat these to see which outcomes come out as the most common, hence probability. And if we list out all the possible outcomes, that's where you get a sample space from. So for instance, if you're looking at flipping a coin that has a side that's a heads and a side that's tails, your two outcomes for the sample space would be heads and tails. That's it. That's all that could happen. And when you go to flip the coin, you don't know which one is going to come out, and that's what makes it a random experiment. Good times. All right, so here's an example for you. So suppose the chances of your business succeeding is 25%. So the experiment would be for you, hey, let's start our new business, and either it succeeds or fails. Sample spaces are usually listed like this as sets. You may be used to the set squirrely brackets that we have there. I just called them squirrely. They're curly. Wow. I don't know what I was doing there. So, and the other bracket used for this are the round brackets. You may be used to either. They're both just an indicator that this is a collection of objects known as a set. Alrighty. So let's look at another example. Suppose the probability that a new hire quits within the first month of the job. I hate this example. Why did I include it? Oh, yep, never mind. I know why I did this. So either they quit or they don't, and your experiment would be, the employee is hired and begins work. And obviously you'll do this as many times as you need to until you keep all your employees. Awkward. All right, last one. Likelihood of the oil well containing oil. This is probably, this is a terrible set of examples because I've just realized they all have one outcome or another. Not everything in the world is either you win or you don't. I know that a lot of things in the world feel like that, but the reason I did all these as two options only is I wanted you to see the probability was not 50-50. In this case, it's 60%. And in the last view, it wasn't 50-50 either. But the idea is that just because there's only two options doesn't mean they're equal. I didn't explain this one at all. I'm moving on. Oh crap, I have one more of these. Ah, yes. 3 or more defects in 1 hour. Either it produces 1, 2, or 3 or more. And we define that 3 or more is 20%. Obviously, that's kind of bad. I mean, that's a high number of defects per hour. Well, I guess it would depend on how many items you produce. We're going to look at more interesting examples of something like this when we hit, I'm saying a lot, when we hit chapter 5, the next one, and chapter 6. They have more interesting examples of multiple item experiments and probability, really. Alrighty, let's talk some more about sample spaces. So usually when we approach this, we do them in the order that I did. If define your experiment, define your outcomes, and then look at the sample space, which we usually abbreviate SS. I've also seen it abbreviated S. That's actually the more common version of it. And also like this weird fancy S that looks like a pile of circles. That looks like this. And this can also mean subsection, fun fact, because that looks like crap. You know what I mean. Maybe you don't because you've never seen it before. Don't worry, that one's kind of archaic. It looks like two snakes sharing a tail and a head. Okay, I'm done. All right. The most common way that we like to organize sample spaces are what are called tree diagrams. So it looks at your defined outcome from your experiment and organizes the repetition of that experiment. So, for instance, let's pretend we're going to draw 3 students and ask them if they like statistics, and we suppose the only answers they could give us would be yes or no. There's our possible outcomes. So we'll define a tree diagram that gives us all the possible outcomes that we could have for that experiment. Woohoo! So on the first student, you ask them yes or no, and they say yes or no, so I'm starting here. And then you kind of proceed down. Then you hit trial number 2, and then you get yes or no, and then trial number 3 or yes or no. And so basically what you do is if you follow a path like no, yes, no, that gives you a list of possible outcomes for the experiment. Now, I want you to pay attention to this outcome in particular because you might mistake it as being the same as this outcome right here because they both have the same number of no's. Now, when order matters, these two are definitely not the same, just like they're not the same as the one down here that has yes, no, no. Because if these individuals are different students, then, you know, the order would matter as to what order they said it in because it would be a different person was saying yes or no, depending on where you were at. So be careful, sometimes order will matter. Now, if we were doing something like flipping a coin and keeping track of how many times a heads came up, then these events would be the same because you're just interested in counting the number of heads instead of the number of tails or something like that. So in this case, if we pretend, you know, yes was a head, they each have a 1 yes in them, so they'd all be the same idea, but there's 3 different ways they could outcome. Interesting, right? Be careful. I have an example later using conditional probabilities and this idea, if you don't like this one, where we actually calculate some things using the tree diagram. And the diagram really does help you keep track of all the possibilities so you don't make a mistake. All right, mutually exclusive events. So mutually exclusive is often confused with independent, and they are actually 2 different ideas. So independent events are ones that have no influence on each other. So knowing the probability of one doesn't affect the other. So basically looking at the 2 events, they are not capable of influencing each other. It's just like saying that your opinion on whether or not banana trees should be allowed to be planted in non-indigenous areas that differs from your neighbor because you guys don't share any land. I am really going off the deep end with this. Independent things don't influence each other. I would like to think that we're all independent of each other and we all, you know, have our own opinions, but at the same time, there are often things that influence our opinions or bias them, so you have to be careful. And when that happens, you get things that are dependent. One of the more interesting studies I've looked at for independent versus dependent has been looking at children and their parents and whether or not they feel like the children's political opinions is influenced by their parents. So what's the most interesting part is that when you see parents that say, yes, we feel like we've influenced our child, but the child says, no, you have not influenced me. It's kind of interesting. Anyway, that was kind of off the rails. Basically, mutually exclusive is if one happens, the other cannot happen. It's just the idea being that, like for instance, eye color. That's kind of a bad one because you can have two different colored eyes. Never mind. That doesn't work. Oh my gosh, I was going to say, let's do hair instead. Nope, that doesn't work either. Here's one that's not mutually exclusive. Ready? Handedness, aka which pen you write with. So you might look at yourself and say, oh, I'm right-handed, and you might look at yourself and say, oh, I'm left-handed, and then say, I can either be right-handed or left-handed. But there are people there and out in the world that can be both. So those events can't be mutually exclusive because there are people out there that are called ambidextrous that are both left-handed and right-handed. Oh crap, I just gave you an example of something that's not that. Darn it. That didn't work so well. Okay, here we go. Better mutually exclusive example. Being a student. Either you are one or you aren't, and you can't be both a student and not a student. Bam! Mutually exclusive. That was better than my example I had for eye color written down. Because yeah, you can't have two different colored eyes. Silly teacher. Here's a one from your book. Sorry. Two events that are mutually exclusive. Basically, all the examples I did at the beginning are because you either can be or you can't be. So either the event A being the well produces oil, and event B being it does not produce. You can't have both occur at the same time because you can't both produce oil and not produce oil. Fun facts. All of mine work for that from me earlier. All right, let's do the business A, business B. Anyway. So basically, business A is being started by a person in North Carolina. Business B is being started in Oregon. I picked them as far away as I possibly could. Clearly, one is on one coast, the other is on the other. They have no influence on each other whatsoever, so we can't say the success or unsuccess of the two have an effect on each other. We're going to see some events that definitely have effect on each other coming up, though. So if you're wondering, like, is everything independent? No. And you should also be very careful not to assume things are independent if you don't know that they are or not. Same thing with mutually exclusive. Be careful. Eyeballs. Dependent events. All right, here's one that's a little easier to see. Hopefully this helps you. So pretend we're looking at a company that has 10 employees, 3 are male, 7 are female, and we're going to select 2 at random at a conference. Sorry, to attend a conference. Event A be the first person selected as female, and event B being the second person selected as male. So you have to be careful with this. So when you go to select your first person, you have 10 people to choose from. But when you go to select your second person, you only have 9 to choose from. So who you draw on the first one, on the first selection, has an effect on what's available for the second choice. And that's how these two end up being dependent. It's just like if I were to draw cards from a deck, if I go to, and I was going to draw 2 of them in a row, I draw my first one, look at it, and be like, oh, it's a 7 of hearts. When I go to draw the second one, the first thing I know immediately is I'm not going to get a 7 of hearts. So that second event is affected by the first one. Definitely dependent. Alrighty, let's talk about assigning probability. So there's some notation down at the bottom here that's very important. So this is the P notation we're going to be using to mean probability for the rest of the class. So be careful. What I've written here is really how you read it. So usually I put quotation marks around this, but evidently they're not showing, so I'll add them in red for fun. Now it looks like I added devil horns to the gene. That's fun. Anyway, so basically we read this as P of whatever event we're interested in. So this is function notation, not multiplication. This is not P times E. It's P of event, So probability of brown hair, or a probability of the business succeeds, or a probability of the oil is being produced. That kind of stuff. I've used this notation already in these notes, but make note of it. This is what we mean, probability of this occurring. So it's shorthand for that. And it's function notation, which I hope you remember. So we're going to look at 3 different ways of assigning probability. The classical one, which I've mentioned already, relative frequency, which is the one people tend to forget about. It's right in the middle. And then subjective, also known as personal probability. So maybe add that to your notes. Personal. Oof. The pen is mightier than, I don't know, my ability to write well. Moving on. So classical is based on what we call counting. It's the ratio of number of ways you can have an outcome over all the possibilities. So this is like when looking at dice, there's one side that has a 3, so and there's 6 sides total on a 6-sided dice, so my probability of getting a 3 would be 1 out of 6, because there's only one way to get a 3, and then 6 because there's 6 possible outcomes, including it itself. So because it's total number, be careful. Don't assume the denominator doesn't include the items from the numerator. It totally does. And this is probably the classical way you're used to doing probability. Ways it can happen out of all the things that could happen. Alrighty, so for instance, if we go back to my drawing employees, the event, oh, I called this A earlier. Oh, no, wait, it was female on the first try. Never mind. No, it was male on the first try. Never mind. New event, E, hey! Our probability of selecting a female employee, so the probability of E would be 7 out of 10, or 0.07. Do we see now why it's a decimal since it comes from a fraction? This is one of the reasons why the percent idea is definitely doable, because you just multiply by 100 to get your percent, and that's what we tend to talk about. But this also tells you why it's going to be every probability is between 0 and 1. The only way you can get 0 is if there's no outcomes or no possibilities in the numerator that can have it happen, and you'll get 1 when the numerator and denominator are the same, which would be that your event you're interested in is everything, or it happens all the time, or it's 100%. So anytime somebody says they're 200% sure that's not their baby, well, that's physically impossible because you're counting and stuff. They don't understand probability. Please don't go to your coach and say, my statistics professor said I can't give 110%. I'm right, but that's okay. They're going to still think you're crazy. Let's talk about some cars. So suppose we have a new car dealer that has the following setup of how many cars they have. We want to select one car at random. What's the probability they have a Nissan? So the first thing you'll do is you'll say, oh, how many ways can I get a Nissan? Well, there's 8 of them, so there's that. And that's what's going to make our numerator. And then to get the total, you've got to add up your values of all possibilities. So 5 plus 6, 11, plus another 3 is 14, plus 8 will give you a 22, plus 2 more will give me a 24. And so we get number of ways to get a Nissan in the top, and then number of ways everything can happen in the bottom, and that gives you 0.33. These are usually pretty simple, and everybody does pretty well with them. This gets complicated quickly, though, so prepare thyselves. All right, relative frequency. So basically, if you repeat an experiment over and over again and record the outcome for a large number of times, you can use that as your frequency of events. So what's interesting about this is how we do things out in the real world. So if you want to ask yourself, oh, I've got a pond out back, how often do I have harmful bacteria in my water? You take repeated samples and record how many you get out of all the helpful bacteria in the water, and that would give you the long run frequency of events. The difficulty with this is if it's something that constantly changes, like your bacteria in your water, it can be more difficult to estimate this with accuracy. But this is often how we'll determine whether or not things are fair or equal. Fun facts. Experimental repetition is really what relative frequency is doing. So here's an example for you. Hey, a pub has to track their beer purchases. So they look at their past 500 purchases, and they notice 150 have been for light beers. They can look at this and say, how often do people order light beer? About 24% of the time. Good times? I don't know why I said that for the beer example. This is how they keep track of any sports like statistics, in case you didn't know. I should have mentioned this earlier. It's fine. So if you have a player that has taken 90 free throws in his past games in his career, and he's made 68% of them, that's how we would find his average for making a free throw. And that would be 68 out of 90, or 0.76. Be careful with your rounding with some of these. I'm using 2 places. Some of the places in your homework, they use other numbers. Alrighty, subjective probability. This is the one I also called personal probability. This is the one where you or I make a judgment call and decide what we think the probability will be. And you know, it's based on personal belief. Now, we should trust personal probability a little bit more when it's somebody who's an expert on the subject in particular, but maybe not so much in the rest of these events. And again, it's a judgment call. So for example, if you're, ordering manager says, hey, I've noticed that in the past about 30% of our sales have been from new customers, that would be probably a good estimate if that person has been in that position for a really long time. It might be a bad estimate if that person has been there for like 6 months. So they've only experienced 6 months of sales. It's not so great. And only 2 quarters. So you know what I'm saying. Keep that in mind. Anyway, so for instance, a manager wants to assess, shipments from a new supplier and whether or not they arrive on time. And they look at several things like, oh, how often have they been on time in the past? What size orders do we usually do? Do we experience more variability with big orders or small orders? What kind of weather conditions are we going to have? Are things less on time when it's bad out, like in the winter and things like that, or when their item is less popular? So there's a lot of things that can factor into this. And it is a judgment call. So I hate to say that personal probabilities are less scientific, but they are, because there isn't a method of calculation. It's making a call on judgment. It's very subjective, hence its name. Jury selection is always an interesting thing in general, but we're going to look at whether or not the jury is going to find you at fault. So suppose you've selected your jury based on the fact that you want them to not find you at fault. And then you look at testimony and evidence and, what their personal opinions seem to be from their interview before the trial. And then you say, oh, the probability they're going to find us at fault, I think, is about 30%. Again, still a judgment call, but if you have an expert on jury selection, this might go better than others. All right, now for the rules. Oops, I forgot to not include this. Sorry. We got a lot to get through. A lot of these are related to each other and interact in interesting ways. Be careful. Notice there are several of these that are for 2 events only. And, they're going to seem a little bit different. This one's also for 2 events. And this one's for 2 events. So we're going to start out with the simpler ones, where we're not doing 2 events, and then we're going to move into doing 2 events. And sometimes it'll be repeating the same event, and other times it will be looking at 2 different things and how they interact with each other. So let's do this. Woohoo! So our first rule is something I've talked about already, and that's everything that we look at, all the probabilities are between 0 and 1. 0 we think is something that's called an impossible event because it can't happen, and 1 we think of as a certain event because it has a 100% chance of happening. Good times. I just drank with you guys listening. That was bad. This is going to be a long video. Especially since for some reason I can't edit things out anymore. Anyway, so if you look at a collection of events that make up your entire sample space, so notice this right here. It says basically these 2 combine to say, hey, when I look at my list of possible events, and they cover all possible outcomes, so when I look at all their probability together and add them, I get 1. This is called the law of total probability. It says if I have everything, it has to have probability of 1 or account for every possible outcome there could be. Get the idea? Let's find out. All right, so let's look at a probability assignment. So suppose you have 3 products on display in a store, and here's the probability that an associate will sell these products in the first 30 minutes of display. So notice that there has been probabilities assigned to each of these values. So for instance, this row 1 is the number being sold 1 has a 30% chance of happening. So if we were to write this out, we'd say P of, well, that P looks bad, P of X equals 1 is 30%. Remember, for us, X is a random variable. So I'm saying, suppose the number sold is 1, and that happens 30% of the time. So you look at all these and you add them all up, and oh, look, it's 1. So it checks out for row 2. Everybody's positive, right? Check, 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 check. All right, good. If any of these were negative or were over 1, we'd be in trouble because you can't have a negative probability. Remember your counting stuff. You can't really get a negative in counting. You don't have -2 of something unless you owe money, but that's also not probability. Anyway. Yay. So what I did there is I added them all up and called them 1. So if you're looking at a bunch of events E sub I, and they each have individual outcomes forming E sub I, then I can actually do an event by just adding up the probability of all of its outcomes. So if I want to make a compound event off of many events, I can add them. Now, this is something that only works if your little e's are all different. So be careful. If you have any overlap, this doesn't work. We'll get into that. So suppose you're rolling a 6-sided dice. You want to find the probability that you get a 1, 3, or a 5. And what you'll do here is E. This is the probability of getting a 1. This is the probability of getting a 3. Those are supposed to be equal signs, by the way. This is the probability of getting a 5. So basically what this says is, oh, if I want to look at the event E, which is these 3 outcomes, I can just add up the individual events that make up E. 1, 3, and 5. Find their probabilities, which are 1, 6, 1, 6, and 1, 6, and then add them together. Fun. And get 1/2. Similarly to the example we did earlier with the associate, if you wanted to do the event that you either sold 2 of them in the first 30 minutes or 3, you would take the event of selling 2 of them, item number 2 is here. And then here's, oh wait, that's item number, 2.4. I was reading that wrong. And then I tried to fix it and I made it worse. There we go, handwriting. And then this is a probability getting 3 because it's a 0.01. Yay. Okay. Now you may have looked at this and said, okay, that makes lots of sense for the first example with the dice. How many ways can I get a 1, 3, and a 5? There are 3 ways out of 6, which would be jumping right to this step. However, looking at this one down below, that's a totally different concept because you can't combine outcomes there. You can only combine probabilities. So it works both ways. Deep thoughts. Whew. Let's look at some investing. So it's actually really typical for you to have a possibility of negative return. Let me pull up the highlighter. That's a little annoying. But keep in mind, it is possible for you to lose money most of the time when it comes to investing, stock options, things like that. So it is possible that when you look at your probability of an event, you end up with a negative return. Scary times. Anyway, so what's the probability of making at least 20,000? Well, there's 20,000 and things that are bigger, so I want to add these two together with my probability. So 0.5 plus 0.2 or 0.7. Be careful when we do more compound events. At least always means the value you are looking at or something larger. A lot of people struggle with at least as far as describing it and thinking about what it means, because when they see the word least, they tend to think that means less than, but that's absolutely not true. I always remember it as, I'm short. For those of you who've never seen me in person, I'm not very tall. And when I was younger, I had a hard time getting on carnival rides because that's something I enjoyed doing back in the day. And so I always reminded myself that this is like the carnival rides. You have to be at least this tall to get on the ride, which means tall, that height is fine, or taller, but not shorter. So that's how you can recognize that this is something that means greater than. Alrighty, let's look at the complement rule. Also is what happens when things don't happen, because this is what we call the not of mathematics. So the way we read this equation is that the probability of not E, so the little bar over top means not. I know it also means mean. Please don't let that confuse yourself. And that means I'm looking at the probability of it not happening. So I want to look at everything and take off the possibility that E happened. So notice you're subtracting off the probability of E. So essentially you're looking at the outcomes that aren't E. And yep. Don't worry about the word corollary. Put little stars and hearts next to this one. It's super important. In general, if something is really difficult to calculate, try complementing it. I don't mean tell it it's a good problem. I mean try not doing it. Okay, don't do that. That's procrastinating. I'm doing way too many math jokes now. Sorry. I mean try doing a complement. Try figuring out if it's easier to figure out the opposite of it and then just do 1 minus, because that'll give you it. And that's usually a little bit easier. So if finding out the probability of odd is difficult, try finding the probability of even. They're opposites. You can do 1 minus and get the other one. That's what the complement rule is up to. And you'll see me use this. I love the complement rule. Okay, so let's look at a complement. This one's a little complicated. Oh, I should have picked an easier one. Yep, that's too many C words. So suppose an inspector is checking 7 products to see if they're defective or not, and there's a possibility of it being defective based on this probability table we have here on the left, and we want to find the probability that 1 or more is defective. So when it comes to 1 or more, that means 1, 2, 3, 4, 5, 6, 7 in this case, and evidently it stops at 7. So what you could do is you could look at this and be like, oh, well, what are the ways this could happen? Well, 1 or 2 or 3 or a bunch of them until I hit 7. And then here's adding them all up. And then you get 0.97. But if you use the complement rule, instead of saying, oh, rather than doing, greater than or equal to 1, what's not in here? Well, stuff less than 1. Or in this case, 0 because, you can't have half a defective. So we'll do 1 minus 0 since that's the only thing that's not in there. It looks like I'm crossing this out. That's bad. And so I'll just do 1 minus the probability of getting 0, which is 0.03, and you get the same thing. So, like I said, if it seems hard, try complementing it. It also usually saves you a little bit of work if the complement event seems more easy. We're going to look at some events, some outcomes in the future for random events that have an infinite list, so it'll start somewhere and eventually just go off to infinity. And when that happens, doing complements end up being a lot easier for doing a lot of our calculations. So this one is one that doesn't go away. It stays and keeps showing up. All right, so if you've never seen a Venn diagram, this rule can seem a little bit confusing, but basically the idea is when you look at two events, if they share anything in common, they have what we call an overlap, and that's what this eyelet piece is making up here. And that's anything where they have in common lies in this space. So when you look at doing the probability of E1 or E2 happening, you have to be careful because you could accidentally overcount the overlap. So when we look at this first probability here, probability of E1 happening, that's all of this stuff. Yeah, and I'm trying to shy this a different direction since it won't let me change colors. And then E2 is all of this stuff. But if I count everything in E1 and then count everything in E2, I've overcounted that eyelet shape. I've, counted this guy, the scribbly-do in the middle, too much. I've counted him twice, once in E1 and once in E2. And that's why we subtract the overlap. Now, if they don't have any overlap, this last term, the E1 and E2, just disappears, so it's fine. So my advice to you is that if you're not sure if they're going to have an overlap or not, always try to subtract the overlap. It'll make sure you get this right. So let's take a look with a deck of cards, and oh my, does this look like a bunch of gobbledygook. So let's suppose you wanted to draw either look at the probability of drawing a red card or an ace. So to do that, you'll add up the possibility of all the red cards plus all the aces and subtract the red aces, essentially. So you can see where each of these parts are coming from. All the red cards would be, well, this total right here, all the reds, that's where the 26 is coming from. And then all of the aces, well, there's 4 of those, that's where that numerator is coming from. And then if you subtract off the red aces, or the cards that are red and an ace, there are 2 of those. And therefore you come up with 28 out of 52, or 7/13. Now be careful, the 2 red aces, if you didn't do that subtraction, got counted twice. So you do need to subtract here. And this is something that's a little bit weird about language for probability versus actual language for people. Notice I said red aces, but what I was calculating was red and ace. So it's 2 characteristics, but most people when they're reading or saying or speaking about this, they'll not say the and, they'll say red ace, even though they're describing 2 characteristics of the card, one for color, one for face value. So be careful about this. When you see 2 words together that don't share characteristics, assume it's an and, because it is. Well, there's no assuming, it is an and. All right. This is the thing I warned you about. If you know your events have nothing in common, aka they are mutually exclusive, then you don't have to do the subtraction. I would caution you to avoid using this rule because it more often than not gets used on accident when it shouldn't. So if you know they have nothing in common, you can ignore the overlap, but I would caution you again to only use it when you know for sure they're mutually exclusive. Be careful, man. All right. So let's suppose you're looking at a clothing store that has 3 styles of work boots. They have 6 styles of A, 12 styles of B, and 2 styles of C. They want to randomly pick a pair of boots and see what's going on. So what's the probability you pick style A or style C? So I've got all the calculated fractions over here. So notice the numerators are based on the style that they have, and then the denominator is based on all the styles together. So 6 plus 12 plus 2 gives you 20. And then I wrote them as decimals. So here, since you can't have a style AB boot or style AC boot, you can go ahead and assume they're mutually exclusive and just add them together. And that's why we're allowed to, just do the straight adding and no subtraction of overlap and come up with the 40%. Be careful, man. Only use this when you should. Let's look at conditionals. So this vertical bar, I have a little note that this means given that. So I think of conditional probability as sort of like in the blind, different from regular probability or classical probability because you already know something happened. So the way you read this is the probability that E1 happened given that E2 already happened. So you're looking at finding the probability of that first event given that you already knew what the second event was, which is a little strange. The 1 and 2 don't work so well here. I like it better with A's and B's. So it's like, hey, I already know something. Can I update my probability? So for instance, what if I asked you, hey, what's the probability that, you have an A in, I don't know, what's a class everybody takes? Finance 101. I know that's not a class at Northwood, okay? I'm just trying to pick something at random. And you're like, oh, okay, well, the chance of having an A are so much out of so much, and, there we go. But what if I told you that the student I was selecting was an honor student? Would your probability change? Yeah. To be an honor student, you have to have a higher GPA than everybody else. So the probability that I ended up with a student who has an A is a little bit higher because they have to have a higher GPA. So see how knowing something changes the probability of your events. So that idea is exactly what's happening in the numerator and denominator here. So if we're looking at the probability that E1 happened, knowing E2 already happened, then I want to look at the probability of E1 and E2 because, well, E2 already happened, that's why it's an and. And I don't want E2 to affect this because it already happened, that's how you end up dividing by it. And of course, I can't end up using an event that's not likely to happen because otherwise this is dumb. It has no effect, which is interesting. Anyway, so again, we're looking at the probability something happened given something else already happened. Let's look at some examples for this. It will make much more sense then. So for instance, if you're looking at a used car lot and 70% of your cars have air conditioner, 40% have CD players, and 20% have both, we can form that into a two-way table, also known as a joint frequency distribution from our chapter 2 notes. Ooh, I almost said the wrong thing. Anyway, so we've got the 40% down below for the total number of CDs, the 70% for the total number that have that have AC, and then the 20% for those that have both. So when you look at this, how I filled in some of the rest of the table is, 20 plus 50 has to make the 70, and then 20 plus 20 has to make the 40, and then this has to be 30 since that's 70, and so this combination happens because those two have to add up to make what's left over for being 1, which is kind of fun. So we want to look at what's the probability that a car has a CD player given that we know they have air conditioning. So notice we're like, hey, I know I selected a car that has air conditioning. What's the probability that they have a CD? So we look at the probability that they had both, which would be that 20%, and divide by the probability that I selected a car that has AC, since I know that already happened, which is why that's a 0.7, and it comes out to the following. Now notice that's higher than the probability of just AC alone, but it's less than the probability, oh no wait, it's less than both of them, I'm so sorry. It's less than them both individually, but higher than the probability of both of them happening. So why is it higher than just the and? Because you know something. To do the and, you got to have both characteristics. And here, you already know one of them happened. So you have more information. That's why it's higher, which is interesting. Okay, maybe it's not interesting. It's interesting because I said so. Ooh, that sounds bad. Sassy times. Mathing. All right. Suppose we look at a company that's 500 employees. 300 of these people have hold college degrees. I did an example very similar to this. Sorry. This almost verbatim was on the final exam last year. So listen up and pay attention. I know we're about halfway where we want to be, but this one's important. I'm trying to warn you. I don't know. Put hearts and stars around this one too, because clearly I like this problem. Sorry. Anyway, suppose 2 employers are going to be selected at random to receive front row parking spaces because, it's nice to give your employees something fun. And evidently walking further from your car to work is annoying. I don't know. I've never understood that one. Anyway, what's the probability that the second person selected has a college degree, given that the first person selected also has a college degree? So there's 2 events you need to calculate here that are actually, you don't have to physically calculate to get this. So knowing the first person has a college degree, what's the probability the second person has a college degree? So notice the order of this. First person has a college degree. Now let's calculate the second. So what's interesting about this is no matter what, the denominator is going to be the same here because you're drawing a person out of your 500 in the first round, and then in the second round you have one less person to select from. And since that first person had a college degree, you have one less college degree to select from. 299 out of 499. What's important about this example is I didn't have to calculate the and to do this or the individual event to do this. I just had to figure it out from looking at how many were available, which is another way you can do conditional probability. Interesting? Maybe. Well, I think definitely, clearly. All right, let's look at a tree diagram example. I warned you this was coming, but hopefully this goes pretty smoothly. So suppose we have a box that contains 5 red balls and 10 white balls. 2 of those balls are going to be drawn at random without replacement. The first thing we're going to look at is the probability the second ball is red. So I'm going to be writing this as the probability that I get red on the second try. So I'm going to put a little 2 down below to mark it as the second one. We've done similar things to this before that, so hopefully it goes okay. And then for the second one, for B, I'm going to be looking for what's the probability that the first ball is white given, oh, this is typed wrong. Crap. Okay, so this was supposed to be the probability that the first ball is white given that the second ball is red. Sorry. Second. So I want red too. So update your notes if you're somebody who prints these out and follows along with me, please. Yeah. Regrets. Anyway, so those are the 2 events we're going to be looking at. Let's make a diagram that organizes our thoughts for this and makes it a little bit easier to do. And we're going to do that on the next tab. All right, so first up, I want to take a diagram. So I'm going to be drawing my first ball, and I've got options of red or white. So for the red one, I have 5 out of 15. If you want to reduce that to 1/3, you can. And for this, oh, sorry, I'm still on the first draw. And for white, it's 10 out of 15. And I did not leave enough room for that. Hold on. Let's erase that part, which is 2/3. I'm going to leave the originals up here, though, too, to help us out with this. So then we go to do my second draw, and my options are red or white, red or white. And so when I go to do my second red draw, my first one was red, so the probability of this happening is going to be 4 out of 14. And if you like reduced fractions, that's going to be 2/7. And then on my second draw, if my first one was red, I should be marking these with 2s. My white will be, well, I have 10 white still because, well, we didn't do anything to the white with our first draw, which is interesting. So that clearly had an effect, but not a very interesting one. Out of 14, because I have 14 balls to select from. So that's going to be 5/7. There's a lot of 7s floating around here. I'm just realizing that. Oh, yeah, because there's one less ball. Ha! That was really loud. I'm sorry. I'm apologizing to no one in a room by myself. Creepy. So out of 14. Okay, so with the second path, if I do white and then white, I had 10 of them, so that means there's 9 now. Ooh, that one doesn't reduce pretty. Sad times. And then white and then red. Oh, I'll have 5 for this one. And that one also doesn't reduce pretty. So now what I'm going to do is I'm going to summarize my results here. So for this top path, I have red for the first ball and red for the second ball. And then the path right below that will be red for the first ball and white for the second ball. Then, oh, I started doing red automatically. White for the first and red for the second. White for the first and, oh no, I want to do red every time. Come on, erase for me. Oh no, it doesn't want to erase. Okay, there it goes. And white for the second. And then I'm going to use the fractions, the probabilities, to determine what's going to happen here. So if you remember what I wanted from A, I wanted the probability of getting red in the second. And there were 2 ways for that to happen. Actually, you know what? I will write out the probabilities for these. This looks like nonsense. I really wish it would let me do color again. It makes this so much easier to understand. So red and red, that would be 1/3 times 2/7. Are we clear where I'm getting those fractions from? I'm just going this top path, which would be 2/21. To do red and then white, I'll get, I almost said red and red, 1/3 times 5/7, which will give me 5/21. All right, now let's look at these last 2 paths, because I'm going to use these fractions in a minute to combine some stuff. So this path would be white and then red, and that would be 2/3 times 5/14. So the 14th and the half can reduce to a 7th. You'll get 5/21 off that too. Yeah, okay. And then this next path will have 2/3 times 9/14. And here we got to be careful. So what I'm doing when I'm reducing these in my head, I'm like, oh, 2 fits into 14. So that'll be a 7, and that goes to be a 1. And then 3 fits into 9. Make that a 1. And that a 3. So that's 3/7. Because 3 times 1 and 1 times 7. Bam. Much nicer. Okay, red in position 2. That happens 2 ways, right here and right here. So I'm going to combine those two. So I'm going to have 2/21 from this value plus, where is it, my second one? 5/21 from that value, which gives me 7/21. That one came out nicely. I likes it. All right, B is harder, and I'm going to try to make it fit. Oh, I'm so sorry. I might have to erase some things. So B was the probability that I get white on the first try, given that red happened on the second try. And this one's a little weird. It would have been interesting to do white 2 and red 1 also. I might do that if I fit it. So my numerator has to be the and of the two of them. So that's white first and red as my second. So the numerator for this is always just the and of this. And then we divide by the given because remember, it's the thing that already happened. Yeah? Okay. And luckily my given is the thing I did in A. So the thing in A was 7/21. I'm trying to make this fit, guys. I'm so sorry. I like it better when I have a blackboard. All right, and then my numerator is white and red, which I feel like I already used that one. Oh, white and red, white in the first position, red in the second. Where is that? Oh, it's right here. Woohoo! 5/21. All right, if you remember anything about fractions, at this step you invert and multiply. When you do that, I don't have space to show it, but your 21s disappear and you get 5/7, which is interesting. So notice that this fraction doesn't occur anywhere else. So that means this conditional, the probability of white given the red was number 2, doesn't occur anywhere else. Yeah, which is interesting. So if you want, you can try some different conditionals. If you want to see some interesting ones, maybe try doing first one red given the second one is red, and second one is red given the first one's red. Sometimes when you flip them, like doing red and white and switch their position for 1 and 2, it totally changes the probability here. It's an interesting thing. Have a looky-see at that if you want to see something more complicated. If you really like this example or want to see another one like it, there is another video with tree diagrams and conditionals like this. I think I do with car accidents and rain, because that's, you know, a pleasant subject for everyone. I just wanted to do one where you weren't drawing things out of a container, because these are so typical and you see them everywhere. Moving on. All right, we already talked about conditional probability. Here is the most important thing. Those of you who go on to take stats 2, you will use this quite a bit. I actually just used it the other day for them, so it's very important. Rule number 7 is very important because it detects something. It helps you determine if events are independent. So if I look at the conditional probability for one event and it has no effect, that means that those 2 events are independent. So to kind of read yourself what's happening here in this thing I'm circling, what it's saying is, hey, if I look at the probability of E1 given E2, I just get E1. What this means is that knowing about E2, knowing the given, had no effect on my probability because it came out the same. This is something we couldn't say from the example I just did because it didn't look like anyone else, right? Yeah, so those 2 are not independent, which isn't a shocker since I was drawing things in a row. Anyway, so this just gives you a tool for detecting independence. So when you're doing this, you want to question the equality, right? You want to calculate this guy on the left side, calculate this guy on the right side, and then see, are they the same? It gives you a way to detect when these are independent, when they have an effect on each other. And that's why conditionals are so powerful and so interesting. They help you detect something. All right, so let's look at an example. So what we want to see here is if gender has an impact on whether or not someone stays with the company for a long time. So this is a way to test loyalty. Another way we'll use this is, oh no, wait, I don't do this in this class. I've also used this to detect customer satisfaction with a product and what impacts satisfaction. And if you go back and look at the smoking status data that we used earlier in the semester, you can totally do this to it as well. So here we go. So we want to look at the probability of male, given that they've worked from 1 to 3 years, versus the probability of male. I really should have written this as a question mark to see if they're the same. So you'll notice that males is 25%. How you can see that is the 50 out of 200. That's where this value comes from, just so you know. Sorry about that. Because you're just looking at probability of male, ignoring the time length one. So then what we want to do is we want to ask ourselves, what's the probability that someone is male given that they've been at the company for 1 to 3 years? So to do this top one, it's 10 out of 200 because the males that have been there for 1 to 3 years is 10 out of the total. And then whether or not they've been there at 1 to 3 years, that's 40 out of the total. So that's where this comes from. And you get 40 out of 20 out of that, which happens to be 25%, which means it's the same as just being male. So knowing whether or not somebody's been at the company for 1.3 years has no effect on their gender. That was a backwards way of saying that. Sorry. Oh, what we want to say is that an employee who's been there from 1 to 3 years is the same regardless of gender, because knowing whether they were male had no impact on whether or not they stayed at the company. Interesting? Maybe, maybe not. What's fun is if you want to switch this, like rather than male here, do 1.3 years and do male there, it comes out the same. Because no matter what, it comes out independent. They are unrelated to each other. They have no effect on each other. And that's why knowing this information that they've been there for 1 to 3 years had no impact. Didn't change the probability from just looking at male. Okay, so where does this formula come from? Well, it comes from the conditional probability, which was probability of event 1 given event 2 equals the probability E1 and really tiny because I got to make this fit, E2 over probability of E2. All we've done is taken this guy and multiply it over here to the other side. And that allows you to get a formula for and. So don't think this is anything magical. That's all it is. So if you have a conditional and you have an original, you can get an and off of it. So this is just another way for you to calculate ands. I actually think this is probably one of the easier rules to use, especially if you know how to do conditionals more easily than others. Let's look at an example. So suppose you're looking at 2 events and you know, oh no, I'm sorry, I'm thinking of a different example. I changed this one. I apologize. So I'm going to have to read this out loud because yeah, this is the one I think it is. Okay. So if you look at a hotel and they have 20 rooms and 5 of them are suites with a living room and 15 have just traditional hotel rooms, what's the probability the 2 rooms you booked during the weekend of the 13th to the 19th, that's irrelevant, are both suites if the bookings are selected at random. So a suite, traditional, so this is just to keep track of this. And then just like we've seen before, 1's for first, 2's for second. So if I want to do the and of suite for the first and the second, I can do the probability of suite for the first and times the probability of suite for the second given the first. So notice suite for the first, that's just 5 out of 20 because, well, there are 5 of them out of 20. And when we calculate this one, you got to be careful because if the first one is a suite, that means you now have 1 less suite to choose from and 1 less room. That's why this is 4 out of 19. Does that make sense? Because the first one was a suite, that means there's 1 less suite available, so there's 4. And because there's only 20 rooms, when we go to draw the second one, there is only 19 to select from. You multiply those together and then do some division. I did do some rounding here too because this doesn't come out whole. It's the same as 1/19th, in case you were wondering. The fraction equivalent to that. Alrighty. Oh, this one, I have regrets. Okay, let's look at a tree diagram with the multiplication rule. So we're going to do a bunch of multiplying here. So suppose we have vehicles that have 2 types of fuel, either gasoline or diesel, and then we have many, many different types of vehicle, truck, car, and SUV. And we have the following probability for their events. Be careful with this. So these are if they're gasoline or diesel, and these are individual events, and here's a bunch of combines. So this is the probability that you have a truck, given that they're gasoline. Here's the probability they have a car, given that they're gasoline. Here's the probability that you have a SUV, given that they're gasoline. And then the same events through, but for diesel. So one thing you may notice for those of you who are interested in automotive is that, yes, probability for a truck, given that it's diesel, is much higher, which makes a lot of sense. There are a lot more diesel trucks than there are non-diesel trucks. So what we want to do is we want to calculate all these ands. So if you look at this and then look at the selections here, you'll see there are multiple ways for you to do this using multiplication. which is kind of fun. So if you're thinking you're beholden to doing E1 given E3, you can actually do this backwards as well. E3 given E1, and then multiply by the other. It's kind of awesome. Let's do this. So we'll set up a tree diagram to do that. So we'll start off with the gasoline and diesel because those are the ones we already know. Then we'll line up our conditionals. So here's the conditionals based on gasoline. Here's the conditionals based on diesel that I grouped before. And then what you can do is you can follow the path by just multiplying exactly like my first tree diagram to get all the ands. Because we know that if I have the conditional for truck given that they're gasoline times gasoline, that just gives us the probability of getting a truck. There you go. Woohoo! And then similar down below, truck and diesel down here. So if you combine these two, you get the probability of having a truck. If you combine these two, is that the one with the cars? Yep, because it's 4. And then if you combine these two, you get the probability of having an SUV. So not only does the table that used this way with conditionals give you a bunch of ands, you can also combine the ands to get all the possibilities for single values. Because if you remember back from the previous slide, we had the individual values for these, but we didn't have the values for E4, E5, or E3 individually. We only had them as conditionals. Good times. I keep saying that when I don't have anything else to say. All right, so I'm going to show you where this comes from, and it's going to be a little bit of symbolic tomfoolery. So if we have two events that are independent, if I look at E1, make sure this matches what I've got down here. Oh yeah, given E2, I know from the definition of conditional probability, this is the probability of E1 and E2 divided by the probability of E2. All right, but if these two are independent, I know this is also equal to, well, just E1 because E2 has no effect on E1. Now, if we ignore the guy in the middle and we multiply this over to the other side, you get that E1 and E2 equals the probability of E1 times probability of E2. We're arriving at this. Now, be careful. For independence only. Erasing never works all that well. There we go. Independent only. Caution. Do not use this rule until you know that your events are already independent. Warning, warning, warning. Red lights, all that jazz. Do not use this rule if you don't already know they're independent, because it makes bad things. All right, let's look at something that's independent. A small Midwestern city has 3 major airlines. Suppose some stuff about which airline it's from, and further suppose that 70% of flyers are for business, and we're going to assume that whether or not you fly for business class is independent of which airline you use. So then what's the probability that you fly United and business? Well, you can just multiply them. That should have been the multiply symbol, which totally came out right. Yay! Now, this is a case where I told you they're independent, so you're allowed to use this. If you're not sure, again, don't use the rule. Good times.